from Francesco some like few weeks or 3 weeks or no 3 months ago, something like that, a huge manuscript which he developed a real theory of this, single-handed, just by himself. I think nobody in the world before him studied this type of question. And we should be very proud that I think our seminar is getting the international premiere of this theory, right, Francesco?
Yeah, yeah.
So with this introduction, I want to introduce Francesco Fournier Facio, who will talk about ultrametric stability problems.
Okay, thank you very much for the nice introduction. And I'm gonna share my screen. Can you see it? Yeah?
Yeah.
Okay. Yeah, and indeed, so the person that had come and asked you for application was Costa, Konstantin Golubev. And indeed, this was a bit more than a year ago. And since then, I started getting interested in p-adic bounded cohomology and then in p-adic stability. But then he sort of quickly realized that all of this is much more general than just p-adics. Is just the important thing that is going on here is this ultrametric word here. And today, so we're gonna mention a bit, start with the more general picture and then quickly focus on compact p-adic groups, which are to make the results more concrete, but everything can be done more general. Okay, so let me start with the general framework, because in this seminar, we have mostly been interested in a few specific stability problems. So just to remind what the general stability question is. So I have a family of groups, which I denote by curly G, equipped with bi-invariant metrics. And by bi-invariant, I mean that the distance between G and H is the same if I multiply by the same element on the right or also on the left. Okay. So, and the gamma, I will suppose that it's a countable groups, just to be sure not to say anything wrong, but this is needed in some cases, in some cases not, but like just to be safe, always suppose that gamma is a countable group. And the stability question is the following. So is every almost homomorphism from phi from gamma to a group in this family here close to a homomorphism? And this is the sort of intuitive way of phrasing stability. But there are these two words here, this almost, oops, let me just be consistent with the color coding. Okay, so this almost homomorphism and close. These are the two words that we need to formalize. So let's make it more formal. So an almost homomorphism, what does it mean that a map is an almost homomorphism? Well, you can formalize this in two ways. The first way is to look at these local defects, so which is the distance between phi of gh and phi of g times phi of h. Okay, so this would be 0 precisely when phi behaves like a homomorphism on g and h. And this is a quantity that is defined for every g and h in gamma. But you can also ask for something stronger, which is a uniform version. So you look at the supremum over all g and h of this local defect. So if you're asking for an almost homomorphism, you might ask that these defects are small for every g and h, but you might also ask this for this smallness to be uniform. And similarly, when we talk about closeness, we have two notions, a local and a global one. So one is the distance at g between phi and psi, which is just the distance between phi of g and psi of g. And then you can ask for the uniform notion as well. Okay. Okay. So
and
these
you take
this
psi
is
to be an actual homomorphism, right?
Yes, in this case, you take psi to be an actual homomorphism. You can, but you can talk about it for any two maps. And yes, exactly. So the definition is the precise definition of stability is the following. So we say that a sequence phi n, which goes from gamma to gn in this group, is a pointwise asymptotic homomorphism. If this local defect goes to 0 for every g and h. But you can also ask for a uniform asymptotic homomorphism, and then you would ask that the global defect goes to 0. Okay? And if you have two asymptotic homomorphisms, then you can say that they are pointwise asymptotically close. If, well, the distance at g goes to 0 phi n psi n for all g, and then you can also ask for the uniform notion. Then you want the global distance to go to 0. And this leads to two formal definitions of stability. So you say that gamma is so G stable, so the family with respect to which you're talking about stability is important. And then you can talk about pointwise stability. So gamma will be pointwise G stable if any pointwise asymptotic homomorphism is pointwise asymptotically close to a sequence of homomorphisms. And similarly, you can ask that gamma is, you say that a gamma is uniformly G stable if any uniform asymptotic homomorphism is uniformly close to a sequence of homomorphisms. Okay, so these are the two general definitions, and these lead to two stability problems. One is pointwise stability. You ask for something local, and you want a local conclusion, right? And uniformly, you ask for uniform stability. You ask for something global, and you want a global conclusion. So if uniform stability asks for has a stronger hypothesis but demands a stronger conclusion. And this is why, in general, there is no relation between pointwise and uniform stability. So, for example, take G to be the family of unitary groups with the distance given by the operator norm that we saw many times in this seminar, especially in the past few weeks. So on the one hand, pointwise stability does not imply uniform stability. And an example is that F2 is pointwise stable, but not uniformly stable. Okay. And so the pointwise stability is, I'm gonna say easy. Maybe it's not easy, easily seen from this definition, but many of you know that there is a definition in terms of presentations, and then from there it's quite simple. It's a very direct fact. And not uniformly stable, this I'm gonna attribute to Rolli. And on the other hand, also uniform stability does not imply pointwise stability. Why? Well, Z2 is uniformly stable, but it is not pointwise stable. Okay. So uniform stability, this is due to Kashdan, who proved this for all amenable groups, but not pointwise stable. This is the Voiculescu counterexample that we've seen, we've talked about in the past few weeks. Okay, so these are two distinct problems, and this is something that I want to stress because it's going to come back later. So in this seminar, we have talked mostly about pointwise stability. Okay, today I'm going to talk also a bit about uniform stability, but Let me just remind you that the main problems that we have talked about were pointwise stability with respect to symmetric groups and the Hamming distance, or unitary groups with metric induced by a norm. And well, since you know that I'm gonna talk about a p-adic analog of this, I'm especially interested in what are the norms that we have put on UN to later find a suitable p-adic analog of this. So let me remind you the 3 norms that we have seen throughout this seminar. So first you have the operator norm. Okay. What is that? The operator norm is just, right, the supremum x smaller or equal than 1, ax. And the important thing that I want to stress here is that this is with respect to the Euclidean norm on C to the n. Okay. Then we have talked about the Frobenius norm, which is just the Euclidean norm on the coordinates. So this is aij squared, sum of the coordinates of a squared square root. So this, I'm gonna describe it as just induced by the inclusion of n times m matrices inside C to the n times n, and then you put again the Euclidean norm on C to the n times n. And then finally we have the Hilbert-Schmidt norm, which is just like the Frobenius norm, but you want the identity to have norm 1. And so you just divide by 1 over square root of n. So normalized Frobenius. Okay. So we have seen talks about each one of these norms, stability with respect to each one of these norms, and we've seen that there are very different behaviors between these. So with the operator norm, we have ended up talking about K-theory, and with the Frobenius norm, we have ended up talking about homology, and with Hilbert-Schmidt norm, we've talked about C-star algebras. And so, you know, for each one, there were different methods that needed to be introduced to prove or disprove stability. So these are the norm that you put on UN leads to the very distinct problems. Okay, so this is the general framework, and I am now going to move to the ultrametric framework. But before that, is there any questions so far? All right. So the question now that I'm going to ask is, what happens if we add the ultrametric assumption? So what happens if every group in the family is ultrametric? And by that, I mean that it satisfies the strong triangle inequality. So the distance between G and H is smaller than the maximum of the distances in GK and KH. Okay. So this is the strong triangle inequality, and this is going to be the assumption that has all the nice consequences that we're going to mention today. And let me, before starting to talk about actual results, let me just show you that this is actually a quite general.
What is K in your notation?
Just any K.
Any K
yeah,
in G.
For all G, H, K in G. Yeah, it's like the strong triangle inequality, but instead of a plus, there is a max. Yeah. And okay, and so let me give you some examples of families of groups equipped with bi-invariant ultrametrics. And there are a few general constructions that lead to families like this. So the first construction is the following. You take G, a first countable profinite group. Okay, so an inverse limit of finite groups. This is a compact group. It has a lot of open finite index subgroups. So you take a nested sequence of open normal finite index subgroups that intersect in the identity. And you choose some sequence of positive real numbers that goes to 0. And then you define a distance as follows. You say that the distance between G and H is epsilon I, where I is the largest integer, such that the images of G and H in these finite quotients coincide. Okay, so G is the inverse limit of the finite groups G mod Gi, and you say that two elements are close if they coincide on a large finite quotient. And the fact that this sequence of Gi converges to, like, goes up to the identity tells you that this is actually a distance, and you can check that it is an ultrametric. Okay, and this leads to certain ultrametrics families that are made of Galois groups. If you add some hypotheses that make these Galois groups first countable, and the groups of rooted tree automorphisms. Okay, if the rooted trees are locally finite, then you get profinite groups that have very natural sequences of nested subgroups, and you can put ultrametrics on these. And another general construction is if you have a group that is acting on a filtered set. So G acts on some set omega, which is a group with a filtration, so a union, an increasing union of sets, such that G preserves this filtration, so it preserves each omega I. Then you do very similar things. So you define the distance between G and H to be epsilon I, where I is the largest, such that the action of G on omega I coincides with the action of H on omega I. Okay, and this allows you to put ultrametrics on, for example, on upper triangular matrices where you let them act on a complete flag. And again, rooted tree automorphisms. This gives you another point of view because you know, they can act on each level. Yeah, so you know, these are two quite general constructions that give rise to ultrametric groups. And the main example for today is a p-adic analog of Ulam stability, so stability with respect to unitary groups and some norm. Okay, so first of all, what is the group? Okay, well,
Francesco?
Yes.
I just wanted to say that there is a very trivial example, which are just finite groups with the discrete distance between them, right?
Yes, yes.
And
No,
this
actually,
was an
yeah,
interesting
any group,
case.
Yeah, any
this
group
is an
with a
interesting
discrete
case in computer science, like all these linearity tests and so on are actually thinking of these groups with this discrete distance.
Ah, okay. Okay, that's good to know. Thank you.
They use a different, they don't use this supremum distance on the functions. They use some probabilistic one. They do the integral, but maybe your techniques may even give you these classical computer science results.
Okay, thank you. I'm gonna ask you for references afterwards. Thank you very much. Okay, right. So the main example that we're gonna talk about today is a p-adic analog of stability with respect to unitary groups. So first, what is the group? Okay, what is the p-adic analog of UN? Well, you know that, I mean, there are many ways in which you could choose it. I'm gonna use this way. So UN is maximal compact in GL and C. So I'm gonna take GL and ZP. So integral p-adic matrices, which is maximal compact in GL and QP. Okay, so this is my choice of a compact, so an analog of p-adic analog of UN. Okay, and then when I want to choose the norm, well, first remember that all of the norms that we mentioned before, like the starting point was the Euclidean norm on C to the n, and that is how you produced all of the different norms. So what is the natural norm on QP to the n now? Well, it is the L infinity norm because we want it to stay non-Archimedean. So QP is equipped with the p-adic norm, which is non-Archimedean. So just saying that it's the induced distance is ultrametric. And if I want to put a natural norm on QP to the n that respects this, I need a norm that also is still non-Archimedean. And so the natural thing to put on it is the L infinity norm. And so keeping this in mind, I'm gonna define this norm. I'm just gonna denote it like this since it's the one we're gonna talk about today. Just the L infinity norm on the coordinates. So this is the p-adic norm in QP. And I claim that this is the correct choice with respect to the criteria I have mentioned before. Why? Well, on the one hand, this actually coincides with the operator norm with respect to QP to the n and the L infinity norm. So it's an analog of UN with the operator norm. It also coincides with the metric induced by including the matrices inside QP to the n times n. Okay, so this is like Frobenius. Then it has a property that I have not mentioned before, but will come back later. And if you know the paper of the Schiff, Glepsky, Lubowski, and Tom that Andreas Tom talked about a few months ago, then you will know that this is an important property. It is submultiplicative. Okay, so this is like Frobenius again. So this is a desirable property. Okay, it means AB, norm of AB is at most the norm of A times the norm of B. So this is good. And it's already normalized. The identity has norm 1. So this is again like Hilbert-Schmidt. Okay, so this is a good norm because it captures properties that all of the other norms, all of the norms that we usually put on UN have. Okay, all of these norms, then the ones that I'm considering. Okay, so yeah, so in some sense, this is the canonical norm to consider on GLNZP. And then another example that I'm not really going to talk about today, but I'm happy to answer questions about later, is just the characteristic P analog. So instead of taking a QP, you can take the field of Laurent polynomials, and then you can take the ring of integers, and you get another compact profinite group, and you can do everything with respect to those as well. Okay. But yeah, from now on, I'm just gonna let G be this family of GLN ZP with the metric induced by these norms. Okay, and I'm gonna study stability with respect to those, but I am always just gonna use what I need to use, and it's gonna be clear from my arguments that everything works in much greater generality, and I'm just focusing on this case for concreteness. Okay. Are there questions so far? All right. So we can now move to stability. And the first general result I want to mention is probably the simplest result. So it's simple enough that I'm gonna sketch a proof. But it's also, I mean, at least I find very surprising, which is a relationship between pointwise and uniform stability. Okay, so remember from before, I'm just gonna go up a bit to remind you this example that we had here. Pointwise and uniform stability are not connected in any way in general. So you have groups which have very finitely presented groups that are pointwise but not uniformly, or uniformly but not pointwise stable. Okay, in general, there is no implication whatsoever. And but now, with the ultrametric assumption, we have the following two results. So let gamma be a finitely generated group. Then, first result, if gamma is pointwise stable, so always with respect to the family above, then gamma is uniformly stable. And if, moreover, gamma is finitely presented, we also have the converse. Okay, so in particular for finitely presented groups, these two problems are equivalent. A group is pointwise stable if and only if it is uniformly stable. Okay? And this is true for any ultrametric family. There is no other assumption of compactness even. It's really any family of groups equipped with bi-invariant ultrametrics. Okay? So I'm gonna sketch the proof of one, and I mean, if you're familiar with these kind of arguments, then you're gonna understand that the same proof works for two as well, like a similar proof.
You know an example of a finitely generated group for which there is no equivalence?
Yes, and it's gonna come later on. Yeah, there exists finitely. So the finitely presented hypothesis here is necessary. It's gonna come in a few minutes. Okay, so one follows from the following stronger lemma. So let's first suppose, okay, let's say I have gamma, which is a finitely generated group, which is pointwise stable, and I want to prove that it is uniformly stable. So what do? I take a uniform asymptotic homomorphism. I use pointwise stability to know that it is pointwise close to a sequence of homomorphism, but this is not enough. Now I want it to be uniformly close, right? And this is taken care of by the following lemma, which tells me if phi n and psi n are uniform asymptotic homomorphisms, and they are uniformly, and they are pointwise asymptotically close, then they are also automatically, they are uniformly asymptotically close. Okay? And this implies one, okay? Start with a uniform asymptotic homomorphism. Pointwise stability tells me that it's pointwise close to a sequence of homomorphisms, and this lemma tells me that it's actually uniformly close. Okay? And I'm gonna sketch the proof of this. So say that gamma is generated by a finite set S, okay? And I take this delta, okay, to be this maximum here. So this I have the defect of phi, the defect of psi, and then I have distance at the generators. So this is a local quantity, right? S is smaller than infinity. And I want to deduce that the distance at any g is uniformly bounded. Okay, I'm gonna prove that it's uniformly bounded in terms of delta. So first step is I want to bound this quantity here. So remember that our notions of defect only tell you about this distance here when you have phi of gh and phi of g, phi of h. So products of two elements. And now I want to use the ultrametric inequality to prove a bound with products of k elements, okay, for arbitrary k. And hopefully I can get a bound that is independent of k. So I'm just gonna say that this is at most, and I do a sandwich here. So phi of S1 up to Sk. I put in the middle phi of S1 up to Sk minus 1, and separately phi of Sk, and then the other part, okay? So this, on the one hand, this is at most the defect of phi, right? This is just a product of two elements, which is smaller than delta. And then here, using the bi-invariance, I can simplify these two, and then I have something which is shorter. So by induction, this is smaller or equal than delta. Okay, and so all of this is smaller or equal than delta. Okay, and this is where where the ultrametric inequality is really coming into play, because if you had a plus here, right, then this induction would give you smaller or equal than k delta. You would get something that depends on k. But here, thanks to the ultrametric inequality, we get something that does not depend on k. And then similarly, with a very similar proof, you have that the distance now you look at this sort of simpler thing where it's decomposed in terms of the generators. Then the distance between phi of S1 up to phi of Sk and psi of S1 up to psi of Sk is bounded by the distance at all the generators, which is at most delta, by the definition of delta. And now if we say that this is actually a sequence of asymptotic homomorphisms, oops, sorry, okay. So if now this is a sequence of asymptotic homomorphisms, right? This is gonna be delta n, and it's gonna go to 0, okay? Because they are pointwise asymptotically closed, so all of these go to 0, and they're finitely many. Uniform asymptotic homomorphism, so all of these go to 0, then delta actually goes to 0. Sorry, here. And I have that the distance, so the global distance now is between phi n and psi n is at most delta n, which goes to 0. Okay. All right, and this is the proof of 1. So finitely generated pointwise stable group is uniformly stable. And now for finitely presented groups, I would like a converse. So I start with a group which is uniformly stable, and I want to show that it's pointwise stable. And this again follows from a stronger lemma, which is that if gamma is finitely presented, then any pointwise asymptotic homomorphism is pointwise close, pointwise asymptotically close to a uniform one. Okay. And this implies too, why? Well, I start with a finitely presented group which is uniformly stable. I start with a pointwise asymptotic homomorphism. This lemma allows me to replace it with a uniform asymptotic homomorphism, and then uniform stability tells me that that is close to a sequence of homomorphisms. Okay, and the proof here is a bit more technical, but very similar in spirit. So you have finitely many relations, and these bounds at these finitely many relations with induction arguments that are not gonna make the constant, the estimate explode thanks to this max inequality. I'm gonna be able to get a bound on all the relations. Okay. And an example, which is in itself, I think, quite surprising, is that free groups are uniformly stable. So free groups are pointwise stable. This is generally true, but uniform stability is often not the case. So for example, it's not the case with respect to unitary groups with the operator norm. This we've mentioned already. It is not true. The free groups are not uniformly stable with respect to the unitary groups with the Hilbert-Schmidt norm. So this is a recent result by Akhtiamov and Dogon. And they are not uniformly stable with respect to symmetric groups and the Hamming distance.
What is this second results that they are not? That
free groups are not uniformly stable with respect to the Hilbert-Schmidt norm. So they proved that uniform Hilbert-Schmidt stability for residually finite, finitely generated groups is equivalent to being virtually abelian.
But for the case of free group, it's much easier because you see a free group. In fact, any hyperbolic group is a second, the bounded cohomology, the second bounded cohomology is non-trivial.
Right, yeah. So this is for the operator norm.
You have a quasi-homomorphism to U1. So already the stability in all norms
that's true. Yeah. Okay.
It fails already in U1.
Yeah. Fair. And okay, so this is actually all Rolli.
I know these results. They are students of mine, but you don't need it for the free group.
That's true. That's true. Yeah. Okay. So actually, yeah. So it all follows directly from Rolli. Yeah, and then Becker and Chapman, who are in the audience, I think, proved this for if a group has finite quotients of unbounded cardinality, then it's not uniformly stable with respect to Sn. Right, but so yeah, just to say that for free groups, actually, uniform stability is not something that is very common, and in this case, it is. in this case, it's always true. Okay, so that was the first and last real proof of this seminar, and I'm gonna move on to tell you about a few other results where we get a bit more interesting examples. So are there questions so far? Okay, so now I'm gonna move on another very peculiar property of ultrametric stability. So this is, I call this section stability with via finite quotient. So the key property of the norm, actually of any ultrametric distance, is the following: that closed balls around the identity are normal subgroups. Okay. So the fact that they are normal is, I mean, not surprising, I guess. I mean, the fact that they are conjugacy invariant is not surprising because the distances are conjugacy invariant. What is very special is that they are subgroups. Okay, in general, in an Archimedean setting, if you do the product of something which has norm 1 times something which has norm 1 is going to have norm at most 2, but it can have norm 2, right? But in this case, we have this very special thing that closed balls are actually subgroups. And this is really follows directly from the ultrametric inequality. So if I do the distance of GH minus 1 from 1, this is the distance of G and H by right invariance, which is at most maximum of distance G1 and distance of H1. Okay. So if I know that both of these are at most epsilon, say, then this implies that this is at most epsilon. Okay. And the really cool thing about this is that now you can quotient out errors. Okay. So if you have an error, bounded errors, you can really quotient them out because they are normal subgroups. So it's in our specific case, the closed ball of radius p to the k is the congruent subgroup in plus p to the k m and zp. So all matrices that are congruent with the identity modulo p to the k. And the quotient is the finite group gln z mod p to the kz. Okay. So this is what I meant by stability via finite quotients. And now what can you do with this information? Well, if you start with a map from gamma to glnzp, which has defect at most p to the k, what can you do? You can just quotient out this defect. And then, so this induces a homomorphism, so a real homomorphism from gamma to gln z mod p to the kz. Okay, so you start with an almost homomorphism, you quotient out the defect, and you get a true homomorphism onto a finite group. Okay, and I basically gave you the proof of the following theorem, which is if gamma is uniformly stable, if and only if its largest residually finite quotient is. And if gamma is pointwise stable, then so is its largest residually finite quotient. And as we will soon see an example where the converse implication doesn't hold. But the first equivalence is what I'm interested in. So a group is uniformly stable if and only if its largest residually finite quotient is uniformly stable. So this tells you that uniform stability reduces completely to residually finite groups. And it also gives you more examples of groups which are uniformly stable. So very trivially, after this theorem, groups without finite quotients are uniformly stable. But I mean, if you think about it, this is very surprising compared to other stability problems. Like all infinite simple groups are uniformly stable, right? Other examples using that free groups are uniformly stable. If you have a perfect group, so a group without abelian quotients, then the root product with Z is uniformly stable because the largest residually finite quotient of this is Z. Okay. Okay, and you also have a similar result for pointwise stability, but there, from pointwise stability, these residual properties, okay, so like residual finiteness, are replaced by local embeddings. Okay, what is a local embedding is just I mean, if you know, good. If you don't, it's just a homomorphism that is locally defined. I won't go into much more detail, but yeah, it's sort of a local notion of homomorphism. So it sort of makes sense that pointwise stability, which is a local something about a local behavior, replaces residual properties, which are global behavior, with local embeddings, which are again local behavior. And the analog of this theorem is the following. So gamma is pointwise stable if and only if its largest LEF quotient is okay. So this is means locally embeddable in finite groups. So this is a very well-studied notion. And it is uniformly stable. So if it is uniformly stable, then so is its largest LEF quotient. Okay. All right. So this is for stability, but actually this approach of studying asymptotic homomorphisms via finite quotients actually also allows us to deal with approximation. Okay. So this is going to be a very brief detour in approximation, which again we've talked about a bunch in this seminar, right? Analogously to hyperlinear groups, right? When you approximate with respect to UN, MF groups, Sophic groups with SN with the Hamming distance. The general definition is as follows. I mean, there are different definitions in the literature, and often they're all equivalent. Sometimes they're not, but this is the one I'm going to use in the general case here. So if I have a sequence of maps from gamma to elements of my family, this is, I'm going to say that it is asymptotically injective if for any g, the basically phi n of g is bounded away from 1. So the infimum of distance from phi n of g and 1 is larger than 0. Okay. And we say that gamma is G approximable if there exists a pointwise asymptotic homomorphism, which is asymptotically injective. Okay. Another way to state this is that gamma embeds in a metric ultraproduct of groups in G. And using this interplay between almost homomorphisms onto the group and true homomorphisms onto these finite quotients, we get the following theorem, which is that gamma is G approximable if and only if it is LEF. In particular, so this is a general fact, finitely presented LEF groups are residually finite. If gamma is finitely presented, it is G approximable if and only if it is residually finite. Okay. Again, this is a full characterization of approximability is very special. So compare this with Sophic and hyperlinear groups where we don't know of any non-example, right? There are very few other approximation problems where we know of non-examples, right? So there are the Frobenius norm, the Schatten P norms for P larger than 1. For those we do know, but it's quite recent and quite involved to produce counterexamples. Here it's characterized in terms of another property that we have that is already studied a lot in the literature.
May I ask you, Francesco, on the other hand, it looks like the GLN ZP has very little to do with this. Like if you take GLN characteristic P, or if you take maybe almost any other infinite family of pro-finite group, which maybe you need it. It contains every finite group eventually. It looks
Precisely.
like not really depending on that's true.
That's absolutely true. Yes, it's the implication G approximable implies LEF works for any ultrametric family of profinite groups. And if your group
probably not for if they're all abelian, then probably not. No.
I mean, no. Also, if they're all abelian, like if gamma is approximable with respect to some family, then you can just some family such that these metrics quotients are finite. Then an approximation is going to give you a sequence of local embeddings that separate your elements.
Right, but the if and only if you probably
yes,
need
exactly.
Now, be rich enough.
Yes, indeed, for the converse direction, you need a bit more hypothesis. And I have examples of, for example, approximability with respect to families of Galois groups of finite fields. I have a complete characterization that is much more restrictive. So the other direction is more restrictive. Yeah, it's a bit more complicated.
So I guess that here, for example, if you change P, there is no difference, right?
No. Here it's really GLN-ZP, GLN-FP, FQ of X. In this case,
also statistic P, and also if it's
also automorphism groups of rooted trees also works the same because they contain all symmetric groups, and So this is all more general. In the case of GLN-ZP, you can get a nice if and only if, but you can get general results in both directions for other general groups. Okay, so this is cool that we have a characterization of approximability, and it's interesting also because it's going to allow us to give non-example of pointwise stable groups. So let me remind you. I mean, if you're a regular attendee of this seminar, then you know this. You know what is coming. So if gamma is LEF and not residually finite, then it is not pointwise stable. So this is an argument we have seen many times in this seminar, that if a group is, say, a group is sophic and stable in permutation, then it is automatically residually finite, right? And here, similarly, if a group is G approximable and pointwise G stable, then it is residually finite. So if you have something which is LEF, so G approximable, but not residually finite, it cannot be pointwise stable. So this allow us to give a lot of examples of groups which are not pointwise stable. So for example, if I start with a finite non-abelian group, then the Lamplighter corresponding Lamplighter group is not pointwise stable. So this is LEF, but it's not residually finite. So it's not pointwise stable. And similarly, another large family of examples is that if gamma is an infinitely presented small cancellation group, then it is LEF. But there are lots of examples which are non-residually finite. Okay, and an example is this group constructed by Pride without finite quotients. So plenty of examples of this kind, plenty of finitely generated examples. And so we get sharpness of two previous results, which I have mentioned already when they appeared. So there exists a finitely generated group gamma. So you can just take Pride's group, such that gamma is uniformly stable, but not pointwise stable. Right? It is uniformly stable because it has no finite quotient, for example, Pride's group, but it is LEF and non-residually finite, so it is not pointwise stable. And also, gamma is not pointwise stable. Let's be consistent with the color coding. But its largest residually finite quotient is. So if I So for example, you take Pride's group, it is not pointwise stable because it's LEF but not residually finite, but its largest residually finite quotient is the trivial group, so which is definitely pointwise stable. And this, right, implies sharpness of this theorem here. Pointwise stable implies that the largest residually finite quotient is pointwise stable. This does not work in the other direction. And oops, not charging. Okay. And also this. If gamma is pointwise stable, then it is uniformly stable, but the converse need not hold unless it's finitely presented. Okay. Okay. So as Alex has mentioned, this is indeed much more general than GLNZP. And in the last part of this seminar, I'm gonna now use a bit more properties of GLNZP, and in particular, P is going to play a role. And we're gonna get more examples that are a bit more special. So before I move on to this, is there any question about this section? All right, so let's move on to now. This section is about restricted orders of finite quotients. So let me be more precise. The key property of GLNZP that we're going to use is that not only it is profinite, so we have already used plenty that it is profinite in the previous part, right? We used that these quotients are finite and this allowed to relate approximability with residual finiteness and stuff like that. But what we're going to use here is that the first congruous subgroup, so this is identity, so matrices that are congruent to the identity mod P, this is pro P. It's a pro P group, okay? So it means it's an inverse limit of finite P groups, okay? This property has quite strong implications. So this is very vaguely is explained in this sentence. So this allows to reduce some stability problems to extension problems of finite groups with kernel a P group. So you know, if you're familiar with stability, you know that stability is very related to lifting problems. And we saw before that finite groups appear a lot. And so if you want to prove stability, you can uniform stability, you can reduce to a lifting problem, and you can, you know, make it so that the groups that appear there are finite. And this fact here, that the first congruent subgroup is pro P, actually tells you that the kernels of these lifting problems are finite P groups. And these kinds of lifting and extension problems with finite groups with some hypotheses on the order are well studied since a really long time. And in particular, there is this following theorem, which is very useful, which is called the Schur-Zassenhaus theorem, that if you have an extension of finite groups where the kernel and the quotient have co-prime order, then this extension splits, right? There is a section, a homomorphic section, and moreover, all splittings are conjugate. Okay, this is a very classical and important result, and it works very well in our context and allows to prove stability of many groups, assuming certain restrictions on the orders of the finite quotients. So let me be more precise about this. So there are two parts of this theorem, right? There is the part that these extensions split, then there is the part that all splittings are conjugate. So for the splitting part, so just the fact that these extensions split, allow to prove the following: that the following groups are uniformly stable. So I'm gonna name them P free, which just means that finite quotients have order co-prime to P. So if I have a group which all of whose finite quotients have no element of order P, basically, then this group is uniformly stable. And here, really, I'm using GLNZP, right? There is this P that is playing an important role. So what are some examples? Well, definitely finite groups without, let's just say, of order coprime to P. These are definitely P3. More generally, periodic groups without P torsion. If I have a periodic group without elements of order P, then there are no elements of order P in the quotients either. And then there is a very large family of examples, which is given by groups acting on rooted trees. So if I take X a finite alphabet and I look at the rooted tree of finite words on this alphabet, then there is a property that is very, has been studied a lot in the past 10 years, which is called the congruent subgroup property. So analogous to what you have with linear groups, which is any finite index subgroup of gamma contains a level stabilizer. Okay, so this is very analogous to the usual congruent subgroup property for SLN thing. Right, so a subgroup of these automorphism group of the rooted tree has the congruent subgroup property if any finite index subgroup contains a level stabilizer. And now, if a group has such a property, then it is P3 for any P which is larger than the cardinality of the alphabet. And there are a lot of examples of this in the literature. It's a problem that has been studied a lot, and in particular, there are all these Grigorchuk groups and generalizations. So Grigorchuk-Gupta-Sidki groups, most of them. So I think there's one exception, but most of them have the congruent subgroup property. And further generalizations of this, there are plenty of examples in the literature of groups with the congruent subgroup property. And so all of these are stable, uniformly stable. Okay, so here I've only used the splitting part, but the conjugacy part implies something which is, I think, even more interesting, which is that stability, very vaguely, behaves well with respect to graphs of groups with some restrictions on finite quotients. Okay, so I'm not going to be more precise on this, but basically the fact that you know that this conjugacy statement of the Schwarz-Zassenhaus theorem basically is going to help you prove stability of the conjugacy relation. And so you can build new stable groups starting from stable groups. You put them in a graph of groups where you have some hypothesis on some finite quotients. You want them to be of order relatively prime to P. And you can deduce stability of the fundamental group of the resulting graph of groups. And in particular, the following are uniformly stable. So these are the examples that where I'm gonna be a bit more precise. So virtually free groups without P torsion. Baum's-Lack solitaire groups, BSMN, where P divides M, but not N. Okay, and this actually generalizes to generalized Baum's-Lack solitaire groups. There is a very easy to check combinatorial criterion, combinatorial arithmetic criterion. So you have the underlying weighted graph of the GBS group, and you check that there are certain cycles such that the weights satisfy something, and this gives you stability. We even have examples which are infinitely presented and are even residually finite pointwise stable. So some kind of properties, that combinations of properties that you want to have. These give examples. So okay, so you just take Z, the additive group of Z adjoined 1 over Mn, and you do the semi-direct product with Z, which acts by multiplication by M over N. If you also assume, with respect to the M and N above, that these are, I mean, just some condition, right? I mean, if you're familiar with Bam's-Lax-Solidar groups, you will notice that this is precisely the condition under which Bam's-Lax-Solidar groups are not residually finite, right? This thing here, and indeed, this is the largest residually finite quotient of the Bam's-Lax-Solidar group. So this follows from a previous theorem. And then we also have some Lamplighter groups. So H breathes product Z, if you assume that H does not surject onto Z mod PZ. Then this is also uniformly stable. Okay. Good. Just a remark, since I think that a lot of the people I'm going to mention are all in the audience. So the result on graph of groups, actually, I did not state it precisely, but it gives further examples of two properties that I think are very interesting and have not been, there are not many examples in the literature so far, but it gives examples of, so constraint stability. So this is a notion due to Arjantseva and Paunescu, who talked about it in this seminar. And very surprisingly to me, because the paper just came out very recently and I had already proved this, so I was very happy to see this definition pop up, which is this stability of epimorphisms, which was defined by Lazarovich and Levitt. And actually, I mean, the epimorphism that is stable is the same epimorphism that is in their paper about stability of virtually free groups. So this gives further examples of these two other properties. Okay, and let me just finish on further on a further specification. So this was only using that these groups are virtually pro-P, but now I'm also going to use that they have characteristic 0, that QP has characteristic 0, because this this only uses Schur-Zassenhaus, so it also works in characteristic P. But when you deal with extensions of finite groups in characteristic 0, it's much easier to work with, right? There you can do more stuff. It's easier for finite groups to have vanishing cohomology in characteristic 0, right? And this works especially nicely. And so replacing the Schur-Zassenhaus theorem with a cohomological lemma allows to prove all of this with a bit more flexibility. So the following groups are uniformly stable. We now get all finite groups. We get virtually P3 groups more generally. So before we had P3 groups, now we have virtually P3 groups. We get finitely generated.
What?
Finitely generated virtually free groups.
I don't think so. I don't care.
So even without the hypothesis on P torsion.
Yeah.
And finally, we get Bam's-Lax-Solidar groups, Mn,
No idea.
where the p-adic valuation of M is different from the p-adic valuation of N. Okay, so before we had finite groups without elements of order P, so that hypothesis is gone. Virtually P3 groups, before we had P3 groups. Now finitely generated virtually free groups, before we had finitely generated virtually free groups without P torsion. And Bam's-Lax-Solidar groups where the p-adic valuation of M is different from the p-adic valuation of N, while before we had p-adic valuation of M is non-zero, p-adic valuation of N is 0. So this is all much more flexible. And again, this generalizes to GBS groups. Okay. So that's that. How much time do I have? Should I stop here or do I have a few more minutes? You're muted, Alex.
No, you still have 7-8 minutes. We are going for
Okay,
75 minutes. Yeah.
Okay, so I'll quickly talk about stability and bounded cohomology, which was actually the starting point of this project. So let me recall the following result, which was talked about by Andreas Thom in this seminar. This theorem of De Schiffer, Gilevsky, Lubotsky, and Thom from a few years ago that says that if you have a finitely presented group such that the second cohomology vanishes for every unitary representation, then it is pointwise stable with respect to the Frobenius norm. Okay, so this is a very beautiful theorem that was used to provide examples of non-approximable groups. And actually, the Frobenius norm is less important than just the. There is a specific property of the Frobenius norm which is important, which is the fact that it is submultiplicative. And indeed, let me remind you, right? This means norm of AB is at most norm of A times norm of B. And indeed, this result was generalized by Lubotsky and Oppenheim to deal with Schatten P norms, which are also submultiplicative. And yeah, so this is the key property. And this property is also satisfied by the norm we're working with over GLN QP, right? GLN CP. So the same argument works, okay? It's really goes through almost unchanged. But there is a special feature, which is that cocycles are bounded. So the cocycles appearing in like the there is some cocycle appearing in the proof, and then the hypothesis tells you that this cocycle is a coboundary. But these cocycles are not bounded. These cocycles are, unbounded, and this leads to using cohomology. Here, the cocycles are bounded, and so we don't have to use cohomology. We can also use bounded cohomology. Okay, which, if you don't know what it is, it's really just you do group cohomology, but you ask for bounded functions, and this leads to a very rich theory, which is quite distinct from usual cohomology. And we're going to state in terms of this, we're going to state the analogous theorem. So gamma, a finitely presented group such that the second bounded cohomology vanishes with respect to every Banach QP gamma module. So this is a QP Banach space with an isometric action of gamma, where this E has a solid norm. So this is a useful hypothesis. It just says that the norm of E takes values in P to the Z. So it has the same value group as QP, okay, which is something desirable, right? Checking only for these is easier. Okay, so if you have this, then gamma is stable. So we get, and I haven't specified if it's pointwise or uniformly stable because I need the gamma to be finitely presented, and we saw that it's equivalent in this case. And so you might be saying, okay, but like, isn't cohomology much simpler than bounded cohomology? Like, why should you go into which it is in the real case? It's much better understood. However, I'm not losing much by going to bounded cohomology, because it turns out that second bounded cohomology, gamma with coefficients in E, actually embeds into bounded cohomology. Embeds into ordinary cohomology. So if cohomology vanishes, also bounded cohomology vanishes. So if you don't want to work with bounded cohomology, you can just work with cohomology. And if you prove a result of cohomology vanishing, this implies the bounded cohomology vanishing, which implies the theorem.
Under what assumption is that the bounded cohomology is inside? You mean for this type of chaotic
Yes.
stuff?
So this is
because this is certainly not the
ultrametric.
case of the real.
Indeed. And gamma finitely generated. So yes, so bounded cohomology is very well developed over the reals, and I have put out a paper in November doing part of the theory over non-Archimedean fields, and it is a general result that for just for topological groups, if they're compactly generated, then second bounded cohomology embeds in cohomology. And so yeah, this is a very special feature of non-Archimedean fields. So cohomology vanishing also gives stability, which gives you a new proof of stability of virtually free groups. Okay. And the other thing that you might be wondering is, well, in this theorem, the spaces were Hilbert spaces and the representations were unitary. Maybe here asking for Banach modules is a bit too vast, too general. And in fact, in the p-adic world, Banach spaces are very restricted, especially if you ask for a solid norm. Turns out that Banach spaces over QP with a solid norm are isometrically classified. So they are all of the form C0 of X. So these are sequences of QP that vanish at infinity. So with the L infinity norm. So although the hypothesis looks like we're asking for vanishing of a lot more stuff, we actually understand this stuff quite well. And this hypothesis that it is a solid norm is important in this setting. And yeah, so I guess I'm done. Thank you very much for your attention. I'm looking forward to any questions.
Thank you very, very much. It was really, really nice. I want to ask a question and to make a remark. Maybe I'll start with a little remark. Lev Glebsky, who is here, and Bharat Rangarajan, who I think he's also here, or maybe today is not here, I don't see. And Nicola Monod and I are now working on developing the connection between bounded cohomology in the real case and the uniform stability. And the situation there is somewhat more complicated, at least as far as we can see. The bounded cohomology itself is not, it looks like the right tool, but it's not exactly the right tool. So we have to take some kind of a twist definition of the bounded cohomology, something that we call among ourselves now asymptotic cohomology, and that seems to be the right tool to study the uniform stability. And it's really interesting that in your case it does exactly the work, but I see that there are really differences. So this is the remark.
Yes, Bharat already told me plenty about the work you're doing. So yeah, so I'm this was also part of the motivation to see if it worked in this setting.
Yeah, another a remark and a question actually. There is, I don't remember precisely, but the Schur-Sachsenhaus, it's very spatial. Now there is a result, I think, a little paper by Dan Siegel, if I remember correctly, who proved that if you have, I don't remember exactly what the result, but if you look at GLN ZP and assume you have a map to GLN, you have another group which is mapped to GLN GLN FP, the finite field, and you want exactly to do this extension, then somehow you have to know that you can make the extension only by finitely many steps, somehow depending on some parameter which I don't remember. And if you can do it, then you can do it all the way to ZP.
Yes.
Have you seen this?
I've seen like various results of this type, but this one I don't know. I don't know of a result of Danziger, so I'm definitely gonna look into it. But these are exactly the kind of results that imply stability in this setting.
I mean, no. This was done many years ago before stability, but I think that such a result can give you an effective connection. You know, what's the connection between the epsilon delta and the stability? Because it's exactly the story in your case. If you can. It can be, if it's true modulo p to the k, then it's true all the way automatically.
Exactly, yeah. So let me mention about this, that all the results that I have, all of the stable groups that I've presented here are all stable with a linear estimate in terms of this delta and epsilon. So they are very good precise estimates for stability. And actually most are really with the optimal estimate. So the epsilon and the delta are the same. And then for these ones in characteristic 0, you get linear estimates.
Do you think that it's possible that whenever stability is true, is always linear, or this look?
No. So something I have not talked about is this finite groups case. In characteristic P, you can prove that Z mod 2Z is stable in characteristic 2 with a quadratic estimate.
Oh, really?
Yes.
That's right.
So there and the various non-examples, like for example Z2. I don't know if Z2 is stable or not, and I would very much like to know. But I do not know if it's stable or not. But I know that if it is stable, then the stability is at best quadratic. And same for surface groups. For free solvable groups, you can prove that the estimate is at best polynomial in the degree of the length of the series and stuff like that.
I see. One question. So okay, it probably also answers, because so it means that if P and L are different primes, so I guess you can find example of group which will be stable with respect to GL and ZP, but not with respect to GL and ZL.
That
right?
is a good question. So I mean, I'm sure that you can, but like what is missing here are negative results that are specific to GL and ZP. So all the non-examples that I have are very general non-examples using this trick of saying LEF and not residually finite. And I don't know of any non-example. I know about many examples that I know hold in characteristic P. So in residual characteristic P for a reason, and but I am not able to prove instability in other characteristics. So, but you know, I very much suspect that, for example, the lamplighter group Z mod 2Z with Z, I know that this is stable in all odd residual characteristics. So for all odd P, I know that it is stable. And I very much suspect that it is unstable in characteristic 2. But I don't know if this is true or not.
I see. Yeah, okay, good. So there's still room for more research in this direction. I mean, I saw your work and I said, oh my God, the guy made a complete theory, so it's not yet complete, which is a good thing.
It's definitely not complete, yeah.
Good. Okay, are there other questions? Please, because I don't see you, so if you want, please speak out. Somebody wants to ask a question. Okay, so if nobody is asking a question, so we'll see you. We'll see you next week. Thank you again, Francesco, for a very nice talk, and it's
thank you for the invitation.
That as a young PhD student, you really develop such a rich theory, and very nice, very interesting.
Thank you very much.
Thank you.